Welcome back, future AI engineers. Today, we're diving into the fundamental technology that powers modern artificial intelligence, neural networks. If you've ever wondered how AI can recognize faces, understand speech, or even beat humans at complex games, you're about to discover the secret sauce behind these feats. Neural networks are at the core of many AI breakthroughs, and understanding them is the first step to mastering AI. So, get ready to unravel the mystery of how machines learn and make decisions, just like us. Let's embark on this fascinating journey together and see what makes neural networks so powerful. Neural networks are computing systems loosely inspired by the biological neural networks found in animal brains. While they don't replicate the brain exactly, they borrow a key idea. Simple units working together can create remarkable intelligence. Think of neural networks as mathematical models that learn patterns and relationships from data, much like how our brains learn from experience. This inspiration from biology has led to the development of systems that can adapt, improve, and even surprise us with their capabilities. By mimicking the way neurons work together, neural networks can tackle tasks that once seemed impossible for machines. At the heart of every neural network is the artificial neuron. But what exactly is a neuron in this context? An artificial neuron is a mathematical function that takes in inputs, processes them, and produces an output. Imagine it as a decision-making unit. It receives numerical data, multiplies each input by a weight, adds them up, includes a bias, and then applies an activation function to determine the final output. This process is similar to how we weigh different factors before making a decision. The simplicity of the artificial neuron allows it to be combined with many others, forming the complex structures that power AI. The artificial neuron operates using a straightforward formula. Output equals the activation of the sum of each input multiplied by its corresponding weight, plus a bias. This formula might look intimidating at first, but it's just a way to combine information and make a decision. The activation function is crucial. It determines whether the neuron fires or not, introducing flexibility and complexity to the network. By adjusting the weights and bias, the neuron learns to respond differently to various inputs, just like how our brains adapt based on experience. To make sense of the artificial neuron, think of it as a decision-making process in everyday life. Imagine you're deciding what to eat for dinner. You consider various factors: how hungry you are, what's available in the fridge, your dietary preferences, and maybe even the weather. Each factor has a different level of importance, or weight, in your decision. After weighing all these factors, you make a final choice, your output. This analogy helps us see how artificial neurons process information and make decisions, forming the building blocks of intelligent systems. Neural networks aren't just a collection of isolated neurons, they're organized into layers. There are three main types of layers: the input layer, hidden layers, and the output layer. The input layer receives raw data, with each neuron representing a feature, like the size or location of a house. Hidden layers are where the real magic happens, extracting increasingly complex features as data flows through. Finally, the output layer produces the final result, whether it's a price prediction or a classification. This layered architecture allows neural networks to build understanding step by step. The input layer is the starting point for any neural network. Each neuron in this layer represents a specific feature of the data. For example, if you're predicting house prices, the input layer might include neurons for the size of the house, the number of bedrooms, the location, and the age of the property. This layer doesn't process information, it simply passes the raw data to the next stage. By structuring data in this way, neural networks can handle a wide variety of tasks, from image recognition to language processing. Hidden layers are where neural networks truly shine. These layers, often numbering in the dozens or even hundreds, extract increasingly complex features from the data. Each neuron in a hidden layer receives input from the previous layer, processes it, and passes it on. This process allows the network to build up a deep understanding of the data, uncovering patterns that might not be obvious at first glance. The more hidden layers a network has, the deeper its learning capabilities, hence the term deep learning. The output layer is the final stop in a neural network. Its structure depends on the task at hand. For regression problems, like predicting a house price, There might be a single neuron producing a numerical value. For classification tasks, such as identifying an image as a cat or dog, there could be multiple neurons, each representing a different class. The output layer takes all the processed information from the hidden layers and delivers the network's prediction or decision, making it the crucial link between the model and the real world. In a neural network, information flows forward from the input layer, through the hidden layers, and finally to the output layer. Each layer builds on the previous one, gradually transforming raw data into meaningful insights. This forward flow of information is what enables neural networks to learn complex relationships and make accurate predictions. By stacking layers and allowing them to interact, neural networks can solve problems that would be impossible for simpler models. How do neural networks actually learn? It all starts with the training cycle. First, data flows through the network in a process called forward propagation, where the network makes a prediction. This prediction is then compared to the actual answer, and the difference is measured using a loss function. The goal is to minimize this error, so the network can make better predictions in the future. This cycle of prediction, error calculation, and adjustment is repeated thousands or even millions of times during training. Forward propagation is the first step in the learning process. Here, data is passed through the network, layer by layer, until it reaches the output. The network uses its current weights and biases to make a prediction. This step is crucial because it shows how well the network understands the data at its current state. The prediction is then compared to the actual answer, setting the stage for improvement in the next steps. Once the network has made a prediction, it's time to see how close it was to the correct answer. This is done by calculating the error, often using a loss function, like mean-squared error. The loss function quantifies the difference between the predicted and actual values, giving the network a clear target for improvement. By measuring this error, the network knows how much it needs to adjust its internal parameters to get better results next time. Backward propagation, or backprop, is the secret sauce of neural networks. After calculating the error, the network works backwards to figure out how much each weight contributed to the mistake. This process involves complex mathematics, but the idea is simple. Adjust the weights so the network makes fewer errors in the future. By repeating this process over and over, the network gradually learns the best way to combine inputs and make accurate predictions. After backpropagation, the network updates its weights using optimization algorithms like gradient descent. These algorithms make small adjustments to the weights, nudging the network closer to the optimal solution. This process is repeated thousands or even millions of times during training, allowing the network to gradually improve its performance. The ultimate goal is to find the set of weights that minimizes prediction errors and maximizes accuracy. Activation functions are the decision makers in a neural network. They determine whether a neuron should fire or not, introducing nonlinearity into the network. Without activation functions, neural networks would be limited to solving only simple, linear problems. By adding nonlinearity, activation functions enable networks to learn complex patterns and relationships, making them powerful tools for a wide range of tasks. The sigmoid activation function is one of the most common in neural networks. It produces a smooth, shaped curve, with outputs ranging between 0 and 1. This makes it ideal for probability-based outputs, such as binary classification. However, the sigmoid function can sometimes cause the vanishing gradient problem, where gradients become too small for effective learning. Despite this, it's still widely used in certain scenarios. ReLU, or rectified linear unit, is the most popular activation function in hidden layers. Its formula is simple. Output equals the maximum of 0 and the input. This makes it computationally efficient and helps address the vanishing gradient problem. ReLU allows neural networks to learn faster and handle more complex data, making it a favorite choice for deep learning architectures. The TAN activation function is similar to sigmoid but outputs values between -1 and 1. It's zero-centered, which can help the network learn more efficiently in some cases. TAN is sometimes used in hidden layers, especially when the data benefits from having both positive and negative outputs. Like sigmoid, it can also suffer from vanishing gradients, but its zero-centered nature offers certain advantages. Softmax is a special activation function used in the output layer for classification tasks. It converts the network's outputs into probabilities, ensuring that all outputs sum to 1. This makes it perfect for multi-class classification problems, where the network needs to decide between several possible categories. Softmax helps the network make clear, interpretable decisions. Feed-forward neural networks are the simplest type of neural network. In these networks, information flows in one direction from input to output without any loops or cycles. They're great for basic classification and regression tasks, providing a solid foundation for understanding more complex architectures. Feed-forward networks are often the first step in any deep learning journey. Convolutional neural networks, or CNNs, are specialized for image processing tasks. They use filters to detect patterns in images, such as edges, shapes, and textures. CNNs are the backbone of computer vision applications, powering technologies like facial recognition and self-driving cars. Their ability to automatically extract features from raw images makes them incredibly powerful for visual tasks. Recurrent neural networks, or RNNs, are designed for sequential data. They have a memory of previous inputs, allowing them to process time series, speech, and text. RNNs are essential for tasks where context matters, such as language translation or speech recognition. Popular variants like LSTM and GRU have improved their ability to handle long sequences, making them a key tool in natural language processing. Transformer networks have revolutionized natural language processing. They use an attention mechanism to focus on different parts of the input, allowing them to understand context and relationships in data. Transformers power advanced AI models like ChatGPT and other large language models. Their highly parallelizable structure makes them efficient and scalable, setting new standards in AI performance. Autoencoders are a special type of neural network used for data compression and feature learning. They learn to represent data efficiently by encoding inputs into a smaller space and then reconstructing them. Autoencoders are useful for tasks like anomaly detection, where finding unusual patterns is key. By learning efficient representations, they help uncover hidden structures in data. Neural networks have transformed computer vision. They're used for facial recognition, medical image analysis, self-driving car perception, and quality control in manufacturing. By learning to interpret visual data, neural networks enable machines to see and understand the world, opening up new possibilities in healthcare, transportation, and industry. In natural language processing, neural networks power machine translation, sentiment analysis, chatbots, and text generation. They enable computers to understand and generate human language, making interactions with technology more natural and intuitive. From virtual assistants to automated summarization, neural networks are at the heart of modern language technologies. Speech recognition systems, like Siri and Alexa, rely on neural networks to convert spoken words into text. These networks also power transcription services and voice-based authentication. By learning to recognize patterns in audio signals, neural networks make voice-controlled technology possible, enhancing accessibility and convenience in our daily lives. Neural networks drive recommendation systems on platforms like Netflix, YouTube, and Amazon. By analyzing user behavior and preferences, these systems suggest movies, products, or music tailored to individual tastes. This personalization enhances user experience and keeps us engaged with our favorite services. In gaming and robotics, neural networks enable intelligent behavior and control. Game AI like AlphaGo and OpenAI 5 has achieved superhuman performance in complex games. In robotics, neural networks help with navigation, simulation, and training, allowing machines to learn from experience and adapt to new environments. These advances are pushing the boundaries of what machines can do. Neural networks are making a big impact in healthcare. They're used for disease diagnosis from medical images, drug discovery, and patient monitoring. By analyzing vast amounts of data, neural networks help doctors make better decisions and improve patient outcomes. The potential for AI in healthcare is enormous, promising faster, more accurate, and more personalized care. Training neural networks isn't always smooth sailing. Common challenges include overfitting, where the model learns the training data too well and fails to generalize, and vanishing or exploding gradients, which make learning difficult. Computational requirements can also be high, with large networks needing powerful hardware and lots of time. Solutions include regularization, better activation functions, and using GPUs for faster training. Ready to build your own neural network? You'll need some basic Python programming skills, an understanding of linear algebra and calculus, and familiarity with data preprocessing. Popular frameworks like TensorFlow, PyTorch, Keras, and MXNet make it easier than ever to get started. Begin with simple feed-forward networks, learn to pre-process data, and gradually move on to more advanced architectures as you gain confidence. Not sure where to begin? Try starting with classic projects like handwritten digit recognition using the MNIST dataset, house price prediction, sentiment analysis on movie reviews, or cat versus dog image classification. These projects are great for building foundational skills and gaining hands-on experience with neural networks. Each project will teach you something new and prepare you for more complex challenges ahead. Neural networks are more than just another machine learning technique, they're the foundation of the current AI revolution. While the mathematics can be complex, the core idea is beautifully simple. Connect simple units together, and they can learn to solve incredibly complex problems. This principle has enabled breakthroughs in fields ranging from healthcare to entertainment, and it's only the beginning. The journey to mastering neural networks is challenging but incredibly rewarding. Every expert was once a beginner who started with that first neuron. As you continue to learn and experiment, you'll gain the skills needed to tackle real-world problems and contribute to the future of AI. Remember, persistence and curiosity are your best allies on this path. Are you ready to build your first neural network? With the foundational knowledge you've gained, you're well equipped to start experimenting and creating your own AI models. Whether you're interested in computer vision, language processing, or robotics, neural networks offer endless possibilities. Take that first step and see where your curiosity leads you. Remember, every complex AI system starts with a single neuron. The most advanced technologies in the world are built from simple beginnings. By understanding the basics and building step by step, you can create systems that solve real problems and make a difference. Stay curious, keep learning, and embrace the journey ahead.